Greetings everyone, my name is Lance, and this is the first video in a series on GPS. If you're new to this topic, you should check out the Wikipedia article, which has some background info, some details on how the system works, some technical info, although that gets pretty deep, and it also has some pictures and diagrams which will explain some of the concepts to you. The image that we're looking at on the screen shows the Earth in the center with the GPS satellites orbiting around it. What I want you to notice is that the satellites are moving. There are 24 satellites plus a few spares, and they're in the mid-Earth orbit, which means they cycle around the Earth twice a day. They're about 11,000 miles high. What that means to you is that the number of satellites you can see from the ground changes throughout the day. That's known as the visibility, and it usually ranges between 6 and 11. If you have buildings or trees nearby, that may block your view, so it may be lower than that, in which case you probably won't get an optimum signal, optimum position fix. These satellites are also sending data to the Earth. They're only sending to your receiver. Your receiver doesn't send anything back to them. The data that they're sending to your receiver is known as the almanac. And the almanac lists all of the GPS satellites, where they're at, what speeds they're at, altitudes, any anomalies from their plane, anything that your receiver needs to know to figure out where the satellites are at. And if it knows where all the satellites are at, it can then figure out where it is. To do that, it uses a process called triangulation. Basically, it's measuring the amount of time it takes for the signals to go from the satellites to your receiver, and the time directly relates to the distance. So if you know where all these satellites are at, and you know how long it takes for the signal to get to you, then you can figure out where that receiver is, which is what it's doing. The problem that comes up into this is that the atmosphere kind of distorts the signal, and it causes it to not move straight. It kind of refracts and bends around stuff. It doesn't actually bend, it just reflects off the atmosphere, and it takes longer to get there. The same thing happens if you look at a piece of glass. If you look at light traveling through glass, you'll notice it doesn't go straight through it, it kind of changes angles. Well, that's refraction, and the same thing happens in the atmosphere. The signals that are coming in may not come straight to you, they may go at a different angle and then come to you. And the problem with that is it takes longer for that signal to reach your receiver, so your receiver thinks it's farther from that satellite. Now there's two major ways to resolve this. One is differential correction, one is RTK. The RTK stuff I'm going to cover in a different video because it can get pretty deep. The differential stuff is quite common, and most receivers on the Earth use differential, at least some form of differential correction. Usually what's involved in this is that there's a reference station, sometimes multiple reference stations, that are stationary, and they pick up the same GPS info that you're getting at your rover. Now this reference station figures out how much delay is coming from each one of the satellites, and so it can kind of get a rough idea of what the atmosphere is doing. And anyway, it sends this correction data to your rover. Now there are two ways to do that. One is to do ground-based transmissions, which is like a beacon signal. If you're in the US, you might be familiar with the Coast Guard beacon, which is what some people use for differential corrections. The other method is to use a satellite to relay that correction info. And the most common method for that in the US is WAAS, which is a system paid for by the FAA. The WAAS system is designed for aircraft, partly to increase accuracy, but mainly to guarantee the reliability of the GPS signal. In other words, if you're flying a plane based on satellite navigation and the GPS satellites freak out, it would be nice to know that the data is bad, which is what WAAS provides them. It can monitor that, and it gives feedback to your receiver telling you that this position is good or bad. Typically, in the last few years, it's been great. It's been used commonly in agriculture for steering. Unfortunately, WAAS is an L1 only signal. It's a single frequency correction system. It's kind of older, so it isn't as accurate as some of the new stuff. It is very good, but it does have a lot of position drift relative to some of the newer correction formats, such as RTK and others. If you're looking at the screen here, you may notice that there's a bunch of squares, and each of those squares represent a reference station spread out through North America. WAAS utilizes 25 reference stations throughout the North America area, and all of these reference stations send their data to one central point, which then pools the information together and figures out calculations for this area. Those calculations then get sent up to a couple of other satellites. You might know them as numbers 135 and 138 if you've been familiar with the precision GPS industry. This screen here shows all of the GPS satellites all throughout the world and what direction they're traveling. You'll see the tail on them that shows you where they've been. You'll notice that 135 and 138 down here don't have tails on them. Those two satellites are in geostationary orbit, meaning that they're much higher They're about 20,000 miles up, and they don't move. They just sit there above the equator. So if you've got a smart enough receiver, a new one, it can also use the distance from 135 and 138 to help calculate position, in addition to all the GPS satellites that are moving. If you look at the legend down here on the right, you'll notice that the different planes that these receivers are on have different symbols. So if you look at the tail, you can figure out which ones are following which ones. All the green satellites on this image are satellites that are being monitored currently by WAS. All of the blue satellites are satellites that are on the other side of the Earth, so they're not currently being monitored by WAS.